You got to be aware of the inbounder here if you're Philly.
It's off to Leonard, defended by Simmons.
May 12th, 2019, Game 7. The shot heard around the world. It was the first ever Game 7 buzzer beater in NBA history. But behind that legendary shot, physics. From the moment Kawhi released the ball, it became a projectile, obeying the laws of motion. Gravity pulled it down, air slowed it down slightly, and the spin he put on it, the backspin, changed how it interacted with the rim. In this video, we'll break down the physics of basketball shots, using real data, real footage, and real science to see how energy, forces, and motion work together to make moments like this possible. Unfortunately, the Kawhi Leonard was not available to help for this project, so I just sourced the next best thing, me. My name is Hunter Gibson, and this is my research project, the physics of a basketball shot. Now, let's dive deeper into that shot. Once the ball leaves my hand, it's basically a projectile. The main force acting on it is gravity, which pulls downward at g equals 9.8 meters a second squared. Horizontally, there's no force, ignoring air resistance, so the ball moves at a nearly constant horizontal speed, which we can see clearly on the x displacement versus time graph. Vertically, gravity makes the ball slow down as it rises, stop briefly at its peak, then accelerate downward, which we can also see clearly on this y versus time graph. The path is a parabola. In equation form, if the ball is launched at speed v0 and angle theta, its height y versus horizontal distance x is this equation. In our case, roughly 6.5 meters out, 3.05 meter hoop height, if v0 is around 8 meters per second and theta is around 45 degrees, this predicts the ball will peak a bit above the rim and travel just about the right distance. In fact, players find that aiming around 45 to 50 degrees is ideal for long shots. A lower angle would make the ball flatter, requiring more speed, while a much higher angle slows the ball too much. There are several forces that act on the ball. First is gravity, which is constant and downward, about 0.6 kilograms times 9.8 meters per second squared, which is around 6 newtons. Next is air drag, which pushes opposite the motion. The drag grows with speed. Roughly, force of drag is directly proportional to velocity squared and follows force of drag equals half the coefficient of drag times the density of the fluid it's in times the area times velocity squared, with the coefficient of drag being around 0.5 for a sphere. At around 8 meters a second, a basketball's drag might only be a few newtons, but it does slightly shorten the flow. Finally, during my shot release, I applied an initial push. Its logger pro analysis that estimates the force was around 50 to 100 newtons during the around 0.2 to 0.3 seconds of release. This push imparted the ball's initial velocity and spin. Next is energy transfer. The shooter's muscles do work on the ball. Immediately after launch, most energy is kinetic. Kinetic energy equals half of mass times velocity squared. For m being around 0.6 kilograms and velocity equaling around 8 meters per second, that's around 19 joules. As the ball climbs, some of that kinetic energy converts to gravitational potential energy, where potential energy equals mass times gravity times height. At a height of around 2 meters, the potential energy is around 12 joules, so kinetic energy has decreased accordingly. At the very top of its flight, kinetic energy is at a minimum and potential energy is at a maximum. Then, on the way down, energy flips back. Potential energy drops and kinetic energy rises. Logger Pro data confirms that total mechanical energy stays roughly constant. Good shooters always add backspin. Why? Backspin stabilizes the fight and even creates lift. A spinning ball drags air faster on one side, causing a pressure difference. Under the Magnus effect, a backspinning ball gains an upward force. This lift counteracts gravity just a bit, so the ball hangs longer. The practical result? The ball approaches the rim more softly and with a better angle. Backspin also helps if the ball hits the rim. A softly spinning ball tends to bounce downward or backward rather than popping out. Coaches often praise the right amount of backspin for that reason. Now, what is the best angle to shoot? Both theory and practice say not too flat but not too high. For a long shot, a three-point shot, around 45 degrees to 50 degrees is best. At around 45 degrees, a given launch speed covers the maximum distance when launch and landing heights are similar, and the ball enters the hoop at a nice angle. Higher angles make the ball go straight up and down. This can work, but needs a lot more force and is harder to control. Lower angles, 30 degrees or less, send the ball almost flat, which can still go in on occasion, but the margin for error is much too small. A basketball analytics study found that the sweet spot is near 45 degrees. If you go too high, slight errors in velocity change the depth a lot. If you go too low, there's little time to correct the flight. In conclusion, shooting a basketball might seem like luck, but it's really physics. The ball obeys the equations of projectile motion and energy conservation. Gravity, air, resistance, and backspin all influence the shot. By using the right launch angle, around 45 degrees, with the proper speed and spin, players give themselves the best chance of a swish. Our Logger Pro data confirm these ideas. The measured path was almost perfectly parabolic, with kinetic and potential energy exchanging nicely and a little lift from backspin.